Hello, everyone. Today, we'll be presenting our thesis project, EGX Financial Advisor using NLP and time series prediction. We've had the pleasure of having Dr. Hossam Sharara as our advisor, and we are very eager to share with you our program. Hello, everyone. Today, we'll be presenting our thesis project, EGX Financial Advisor using NLP and time series prediction. We've had the pleasure of having Dr. Hossam Sharara as our advisor, and we are very eager to share with you our progress throughout this semester. Okay, so to give you a brief idea of what our thesis project aims to achieve, um, the main goal for our thesis project is to predict the price time series for each of the EGX30 companies, given the information which is most likely going to affect these stocks. So, drawing from technical analysis and how the general market sentiment very clearly affects the stock market, we took into account three major factors, namely the price time series, the financial quarterly data, and financial news. Price time series is essential, as not only today's price affects tomorrow's or even other future prices, rather trends are prevalent in the stock market. And for those of you who may not know, certain market trends tend to move in a particular direction over a certain time. This may occur due to general speculation, financial condition this specific market tends to go through during certain times, or even trends that are solely based on the price, which happens when a stock is nearing a milestone in terms of its price, for example. Other than that, financial quarterly data was also an essential element to take into consideration, as stocks do not solely perform based on the prevalent market sentiment and price trends, but rather stocks are very reflective on the financial performance of the associated entity, as stocks are representatives of the ownership shares for that entity. Therefore, it is intuitive that if a company released a quarterly report indicating high financial performance, it would attract more shareholders, increasing the demand and consequently driving up the price. Similarly, the opposite happens when a company underperforms. Finally, financial news is one of the biggest determinants of stock prices, as they are representative of the current market sentiment. The stock market could be looked at from a supply and demand perspective. Therefore, if a negative sentiment is detected, it would make sense that the shareholders would not be likely to hold on to their shares, and the opposite is true when it comes to when it comes to market sentiment. Using all of these determinants and based on the aforementioned justifications, we attempted to predict time series for the time series for the price of each stock using NLP and time series prediction. Okay, so in order to achieve all of that, we first had to go through a vigorous phase of data collection. So basically, the data we acquired was divided into two parts. We needed the historical financial data and historical financial news articles. We scraped a number of popular sources for for Egyptian financial news, including أنوار الغد, مباشر, البورصة نيوز, and جريدة المال. These specific news sources were chosen after a few days of researching, we saw that these were the most prominent financial news sources here in Egypt. So it would make sense that these news sources are more likely to move the market sentiment better than others. So we collected the historical news articles starting from 2012. After this year, we collected the news articles in Arabic, and along with some metadata, including the title, the author, date, time, and so on. Okay, and for this task, we utilized a number of scraping tools, which some were more appropriate than others, more faster than others for certain website structures, as this was a scraping task. So we needed to try a few things to have the data getting here faster. As scraping is very, very time costly. We utilized Beautiful Soup, Scrapy, and Selenium. And finally, for the financial data, we utilized the university's access to Thomson Reuters labs to access financial data, including daily prices for each stock, financial ratios, including cash flow per sales, dividends per share, earnings per share, market value, total return index, turnover by day, and finally, the raw data that was extracted from quarterly reports.
We first concatenate all the articles posted each day into one string, then we process each day's text as follows. The first step is the tokenization step, which is basically dividing the string of words into an array of substrings, and those substrings are either words or special characters, and we refer to each substring as a token. And the second step is to remove the stop words from the tokenized array. Those stop words consist of words that are not related to the text context, such as the pronouns or al-dama'ir. Also, we include punctuation symbols in those stop words. And the last step is to stem each word in the text, which is basically retrieving the root of the token by removing its prefix and suffix.
Our initial thought was to create two models. The first is to understand the article's sentiment using BERT. Then we would feed that sentiment to an LSTM model that is trained on the data, the stock market data. However, we have discovered that this approach was not an adequate one because of certain limitations presented to us by BERT. The first limitation is that it is not pre-trained to fully comprehend financial data, which invalidated our plan since we wanted two separate models. However, since it's not fully trained on to comprehend financial data, that created a certain struggle. The second thing is that we struggled to correlate data between companies, which means that every company had its own model. That model had a sentiment analysis, then it is fed to an LSTM model, which was not the ideal case since we could not correlate data, and we all know that financial data is correlated together because the stock market is about news, and news do not only affect one company, it affects more than one company. Which takes us to our third limitation, which is that when we created a time series, there was a limited number of the data entries per company, because we only have a limited number of articles that is talking about that specific company itself, and since we do not have data to correlate, then every company had exclusively a set of data, which was not enough. Our final limitation was that BERT only accepted 512 tokens, which means that if an article surpassed 512 words or tokens, that was a struggle for us, since by that we had to create a sliding window technique, which wasn't the ideal case. All of these limitations led us to change our approach. We were tempted to try different approaches until one of them provided us with the most adequate or the best F1 score and precision, which is why we reverted to trying other techniques.
Our first embedding approach was bag of words. So what bag of words essentially does is it represents text as a vector of word occurrences, as shown in the image in the top right corner. To do so, we first concatenated all of the pre-processed daily articles into one string that represents the articles of that given day. The array of strings is then passed through sklearn's count vectorizer. This tool returns back an array of vectors, which is essentially the bag of words, and a dictionary with all unique words found. This approach caused many problems and wasn't the most ideal embedding approach. This is due to how large our dataset was. The bag of words process resulted in a dictionary size of 80,000 words. As a result of this large dictionary size, the dataset was huge, and this led to slow training times. Moreover, each vector was sparse, as all of the vectors mostly consisted of zeros due to the dictionary size. And all in all, this method led to a poor model accuracy of only 43% and an F1 score of 18%.
So moving forward with training our model, we are presented with an issue that the article data we collected, as previously discussed through scraping, is text data, which is also incomprehensible by the model since it's not numerical. The other issue which we faced is that the raw text collected from the articles is of variable length. Not all articles have the same length. Therefore, it would be problematic to train on this data directly. So in order to solve this issue, we used DrVek, where its end goal is to produce a matrix which is of a constant predefined length and is numerical, thus solving these two issues just outlined. So DrVek provides a way to reach the goal that we want, which is, however, while also keeping the context of the articles and the weights of the words in each article intact and preserved in our end goal matrix. So DrVek is basically another implementation of a Word2Vec, the popular Word2Vec technique. So we trained actually our own embedding of DrVek, and in order to give a better overview basically of what it does is that it identifies every document first with a unique document ID, and it takes all the words within the documents after and numerically represents these words through, for example, one-hot encoding. We then mask a word and look at its neighbors from both sides in order to predict the value of what that word would be. This is basically the continuous bag of words technique. You would then keep training the model until the predicted words produced by the model are accurate. We train on this data in order to optimize the relation between the words and each other within documents in order to get the similarities between articles optimally. So the model described above is basically called the distributed memory version of paragraph vector, or PFDM for short. So in order to test our own implementation of the embedding of DrVek, here you can see that we inputted the article shown above here, and our implementation then derived that the below article is most similar to it, which you would also verify by reading both articles. And you could also use that in order to verify that our own implementation of the embedding of DrVek actually works desirably to what we want to achieve. We mainly use DrVek in the end instead of a bag of words in order to fix the issues which we faced with bag of words as described before, and also because DrVek is generally a more accurate approach, where the error rate in the bag of words is almost double than that of DrVek. Therefore, we choose to move forward with DrVek, and actually DrVek caused more than a 25% increase in the F1 score in our end model.
We have attempted the different strategies to achieve our goal, and we started off with using baseline models. We first appended some historical data for each company to the input features beside the text embedding vector, and that's to enhance the model's performance. Data such as the average percentage change for the past week, percentage change of the previous day, stock closing price of the previous day, and the average stock closing price for the past week. And we first tried to approach this as a regression problem by using different models like regression trees and linear regression, but this approach did not yield the desired results as the baseline models were not capable enough. Then we switched to a classification approach by trying to predict which class under which the percentage change of the closing stock price will fall. Thus, we binned the percentage change labels into 5 classes consisting of weak negative percentage change, strong negative, neutral, weak positive, and strong positive. The decision trees approach produced the best results with accuracy of 76.8%. The accuracy is not very indicative here as it is kind of sensitive to the distribution of data in each bin. Thus, the F1 score would be a better indication of the performance of the model, and we achieved the F1 score of 65.8% which is actually better than the random chance, and the precision and recall are 66.7% and 65.3 respectively. We also tried neural networks, but the results were not very favorable. Also, we analyzed the mentioned metrics for each company separately, and we found out that the performance varies for each company and this is a problem that we are gonna tackle in the future.
Now, on to the next section of our presentation. We describe the latest model used. The Temporal Fusion Transformer model is a state-of-the-art time series prediction model developed by Google Cloud AI in 2019 that incorporates multiple established techniques. In our implementation of the model, we input the different indices as a feature, along with the article embeddings, quarterly reported ratios, and engineered features such as the day of the week. This helps expand the number of instances entered into the model, solving a common issue in time series prediction tasks in general. This is because despite 10 years of samples seeming like a lot, this only amounts to about 3,500 observations. This model allows us to input the index as a static categorical feature, expanding the number of observations to 30 times that, because we have 30 indices, which is about 100,000 observations. This also maintains cross-index learning, as patterns in one index at a specific point in time can affect other indices, improving the results. This deep learning model contains three main layers that enable good performance on time series tasks. Firstly, a static encoder layer to integrate aforementioned static features into the network through vector embedding. This data is then propagated onto an LSTM layer to locally process observed inputs on a shorter term basis. Then, there are transformer encoder layers with multi-headed self-attention that circumvent RNN's vanishing gradient issue. The purpose of this layer is to determine which previous observations should be most relevant to the current prediction at hand. Going into further detail into the model architecture, its main objective is to learn both long and short-term temporal relationships from both observed and known static and time-varying inputs. A sequence-to-sequence layer is employed for both local processing, whereas long-term dependencies are captured using the multi-headed attention block. LSTM encoders are employed for past inputs and decoded to infer the forecast. The model architecture also employs a gating layer to essentially suppress unused components in the architecture in case a type of input is lacking. The output is finally propagated into a fully connected layer before producing forecasting predictions. Now onto the initial results obtained after training this model. Here we can see the best performing predictions over a period of 30 days. As can be seen, there are sections where the predictions can be very close and others where the predictions do not match the actual outcome. This will require a more detailed analysis in the future. On the other hand, the model failed to predict some indices reliably, as can be seen here. We suspect that this could be due to a lack of data. However, this will require further analysis to reach the reasons why. Here we can see that the four most important variables used by the model were the index as well as previous closing prices scaled differently. On the right, we can see the scaled average prediction of each of the 30 indices separately. In conclusion, when evaluating the model metrics as a whole, we saw that the R-squared metric significantly varied by index, where some indices were close to zero or negative in some cases, while others produced a slight positive result, indicating a correlation between the actual and predicted outcomes. This will again require a more fine-grained approach, which we intend to do in the future, specifically in Thesis 2. To summarize and conclude, we went through our tests, both successful and unsuccessful, our approaches processing the news articles, the baseline model we will use as a reference, and finally, a more advanced model we experimented with its results. In the future, we will work on improving the forecasting, as mentioned before, and the empowerment outcome will now be discussed.
The empowerment outcome of our thesis project solely depends on the accuracy of our model. Our main goal is to reach state-of-the-art stock price prediction. By achieving this goal, we will be able to deploy a financial advising platform that's powered by our model. Access to the platform will be subscription-based and available for independent stock traders and hobbyists. They'll be able to subscribe to our service on a periodic basis. Our service will provide them with our best stock picks that should yield the most profit. We will also provide prediction graphs for each EGX30 company. The second part of our service will be available for commercial use. Companies can subscribe to our API service to get access to our private APIs. They will pay a base subscription fee and a small fee for each API call. But in the case we do not reach state-of-the-art accuracy rates, we will go for the community deployment route. Our plan will be to open source our software and publish it on GitHub. We will give people full access to our code and the datasets we compiled. By doing so, we will be giving people the opportunity to contribute and improve our model. Contributors can even take our source code and implement it for different stock markets.